Hi, and welcome to our new session here in our chapter on information theory. So this session here will be on many more details regarding joint entropy. We'll introduce conditional entropy, and then the major, goal of this introduction here is figuring out what mutual information is. And there will be 2 sessions on mutual information. Yeah, this is, I guess, the first one. Yeah, okay, so let's start with this. So I said that I would also discuss joint entropy here, so I already did that before. So I already introduced joint entropy for the discrete case and also for differential entropy, but as a short recap. So here, this is a formula for joint entropy for the discrete case, and this is our formula for joint entropy for the continuous case. And there's not a lot of, exciting or surprising stuff going on. We just, working on the bivariate density, and we also said that we can also do this for n variables and not only 2. Okay, so it's exactly the same formula as for the, or it's a straightforward generalization of the entropy formula when it acts on a single random variable. And for the rest of this section here, I will pretty much exclusively only discuss the discrete case and pretty much everything, and I cannot even come up with a counterexample. Everything that we show here and discuss works in a completely analogous manner for the continuous case. So we simply have to swap out, as always, sums for integrals. Okay, so the first thing I would like to do now is to introduce conditional entropy. So conditional entropy, I would write as eta of y given x. So this should quantify the uncertainty of y that remains if we already know the outcome of x. Okay, so hopefully you can also now very soonishly see that there's a straightforward and very direct connection to conditional distributions and conditional densities, conditional random variables. So we now define the conditional entropy as the expected value of the, we define this as the expected value of the entropies of the conditional distributions when we average over the conditioning random variable. Okay, that sounds complicated, but it actually is not. So let's take a look at a pair of random variables, x and y. And of course, we will assume that they are specified by a bivariate density. And if this is here discrete, this would be a bivariate probability mass function P on x and y. Now, the conditional entropy eta y given x, I will define as this expectation here. So I will take a look at the entropy of the random variable y conditioned on, that's correct actually. We'll take a look at the entropy of the conditional random variable y when I condition on x equals lowercase x. So this here, this is also a random variable, okay? And this has a probability mass function that I can easily compute, right? And because of this, I can compute the entropy of that thing. And what I will now do is I will average the entropy or compute the expectation over all of these entropies when I average out over the distribution of x, okay? Which I can write like this here, So this would just be my discrete expectation. And I can write it like this, where the only thing I've now done is I have inserted or plugged in the definition of the entropy formula when I'm working on this guy here. So I now have to use these conditional probability mass functions, so not P of y, but P of y given x. And now I will simply, merge these two guys here, so P of x times P of y given x, So I put them together to this joint probability mass function here. And this is exactly the formula I would like to arrive at, because this is here exactly this negative expectation of log of p of y given x. Okay. So I can also write this down for the continuous case, which is, as I said before, completely analogous to the discrete case. Good. So what can we now do with that? So the first nice thing we can do with the conditional entropy is that we can derive the so-called chain rule for entropies. So there's the chain rule for probability densities, and actually we just use that. So maybe let's write that down. For, as always, my pen tool is not working. So I can, for example, write that down for densities like that, right? So this here is the same as p of x now multiplied with p of, maybe I should actually use a y instead of an x too. Okay, I guess depends on how many of these guys I want. Okay, but for the bivariate case I'm using x and y. So maybe let's do this here as well. So I have p of x comma y, and this is the same as p of x now times p of y given x. Okay, so this you should know from basic probability theory, and there's now a similar chain rule for entropies, and because entropies in a certain sense are defined on log level, so this product here is turned into a sum. Is it easy to prove that? Answer is yes. Proof is down here below, so I'm not sure. Well, maybe I'm going to read out everything, so it's not super exciting. What happens here is actually very easy to show. So we start with our joint entropy. We plug in the definition for the joint entropy. We now use the chain rule for densities, which we have just discussed. And this p of x times p of y given x happens now inside of a log function. So we can use the property of the log function that it turns product into sums. So I'm doing this here. Yeah, I'm also redistributing these sums over the x's and the y's into these two terms. And the only remaining thing I'm now doing, let me check that, is, well, if I take a look here at this first term, yeah, I can see that there's this p of x in here that does not depend on y, so I can simply take a look at this inner sum. So here I see that I have the joint density, but I'm summing across all the values of y. So in some sense, kind of summing that or integrating that out. I guess I shouldn't say integrating, summing it out. So this will then result in the marginal p of x here. And for the second term, I just do, well, I do this in reverse. So let's check that. So I have this thing here. So I have the conditional, copy that over here. Yeah, and then I'm just an idiot. I have this here, so I just do nothing, right? So I just copy that over. And now if I look at these two resulting formulas here, so here I have the entropy of x, and here I have the conditional entropy of y given x. It's also an n variable version. We do exactly the same thing for n variables, and it looks exactly analogous to what happens for the factorization of densities. There are a bunch of very, very simple conclusions from this, corollaries. So first of all, the joint entropy between x, x is simply the entropy of x. The conditional entropy of x given x, which is 0, and the entropy of the conditional entropy of x comma y conditioned on z is the entropy of x conditioned on z, and the entropy of y conditioned on x and z. And this is exactly the same formula as before, when you just condition everything on all sides on z. And I'm not going to prove this here. You can try this out yourself, and you should be able to do this in very, very few lines, very often just one. Another interesting observation, so if the conditional entropy of x given y is exactly 0, then we know that x is a function of y, so that for all y, where we have a positive probability for all lowercase y, so for all categories of y, there is only exactly one x so that in the joint probability mass function p of x comma y, there's positive probability. Okay, this is exactly what a plausible definition of x as a function of y means. This is not very hard to prove. It takes probably a little bit more than one line. This is actually maybe a very good exercise to test yourself if you want to prove that. Okay, so with all of these kind of, I don't know, technical lemmata that we have now discussed, and based on this notion of conditional entropy, we can now finally define what we mean with mutual information. So the mutual information should describe the amount of information of one random variable obtained through another random variable. Another way of seeing this is also how different their joint distribution is. So if we have two random variables, how different is their joint distribution from a purely independent case where the joint distribution factorizes into the marginals. So let's now consider two random variables x and y. They have a joint probability mass function p of x comma y, and of course they also have marginal distributions p of x and p of y. The one way now to define the mutual information, which we'll denote with I x semicolon y, so traditionally it's written that way. One way to define that is basically the Kullback-Leibler divergence between the joint distribution and the product of the marginals. So this here, okay? And you now can write that as this formula here, which I'm not going to read out, or you can also define it like that here as this expectation, which is simply our definition of the Kullback-Leibler. And we can also do this for continuous random variables like that in a completely analogous manner. So I guess we are not very sure yet. I guess this here should hopefully make sense. Yeah, so this distance between the general joint case and the factorizing case of pure independence. So measuring this distance from independence, I guess you might see as something reasonable, but I guess it's a good idea if we derive now a couple of more properties. So there's one extremely important relationship between mutual information, entropy, and conditional entropy, and this is also exactly why I defined conditional entropy in this chapter, which is this here. So I can say that the mutual information between x and y is exactly the same as the entropy of x minus the conditional entropy of y of x given y. Okay, is that easy to prove? Answer is yes. So we start out with our, I don't know, weird current definition of mutual information that we haven't understood so well yet. Yeah, I can take a look now at this thing here. Specifically, I can take a look at the joint p of x comma y divided by the marginal p of y, which is the same as the conditional PMF p of x given y, then divided by x, because that still remains. Again, now I can use the property of the log function, and in this case, let me take a look at this. So Now I'm confusing myself a little bit. So this log should actually... okay, I'm just an idiot because I thought okay. So this log function will take apart this quotient here into a difference. This is the positive term and this is the negative term. So here we have the conditional density and here we have the marginal, which we now have to negate. And then the only thing that remains is, let me remove some of the scribblings. So the only thing we now have to do is we have to see that in, the first term, again, we have this here. We sum out the y. The second part doesn't even depend on that. So this becomes the marginal now, and now we are done. So this is for the first part. So this is now simply the formula of the entropy. And in the second part, I guess we basically do nothing, because we already have the formula for the conditional entropy of x given y in front of us. So we can now interpret, we have this very nice relationship between three important concepts, so mutual information, entropy and conditional entropy, but we can also enjoy a further understanding of mutual information as the reduction of uncertainty in x, encoded through the entropy, due to the knowledge of y, which we would encode as the conditional entropy of x given y. So I guess this is exactly what the formula tells us. Here are some further simple relationships. So this is what we just proved. And because mutual information, as you should very easily see, is a symmetric function, you can do exactly the same the other way around. So we can also write it as entropy of y minus conditional entropy of y given x. From the first two formulas, it's very easy to see how we can bound the mutual information from above. So it's obviously bounded above by this thing here. It's obviously bounded above from this thing here. So it's bounded above by the minimum of the two. Again, using these two relationships, we can also derive this nice little formula here. So the mutual information between x and y is the same as the entropy of x plus the entropy of y minus joint entropy of x comma y. Symmetry we already discussed, and mutual information between x and x is the same as the entropy of x. Again, if you want to have a couple of nice little test exercises, prove all of these things yourself. It shouldn't take more than, 1 to 3 minutes for each of these. So let's wrap everything up now with a very concrete example. So you can check that we can also easily compute all of these things ourselves. So here is a simple joint distribution between two discrete random variables x and y. So apparently both of them have 4 classes, 4 categories. I've specified the joint probability mass function through this table here. Of course, we can now easily compute sums in rows and columns to compute the marginal distributions of x and the marginal distribution of y. So I don't know, maybe we can do this for x1. So we sum over this column here. So this is 1 divided by 6 twice, which is 1 divided by 8, plus another 1 divided by 8, which is 1 divided by 4, and plus another 1 divided by 4. And this is exactly 1/2, which we have here. You can check that for the remaining values also for y. We can now easily compute the entropy, because you should hopefully remember the formula of the entropy for x and y. You can see here the entropy is specified in bits. So for x, eta of x is 7 divided by 4, and for y it's exactly 2. And as I'm specifying this in bits, I have used the log with respect to base 2 here, obviously. And we can now compute also the conditional entropy of x given y by simply putting our definition of the conditional entropy to use. And I guess I'm not going to read that out. So what do we have to do here? Well, we need the marginal of y. We had that on the slide before, and we now need all of these conditional distributions of x given y, or a certain value of y. Fortunately, we can simply take a look at our joint table. So what we basically have to do is, if we want to do that for, we want to do that for x given y. So let's maybe say y equals 1. That means we have to look at this row, and then the only thing we have to do is we have to normalize this row, and you should easily be able to check, well, because we already know what the conditional of y is, we also know what we have to normalize with. So basically have to multiply every value in that row by 4, and apparently very nice that we have to do this for every other row as well, because the marginal distribution of y is always 1 divided by 4. So if we do this, the first entry is going to be 1 divided by 2, then 1 divided by 4, then 1 divided by 8, and then again 1 divided by 8, which is exactly what we have here. And I'm now too lazy to do this for the other entries. So you can check this yourself, or you can just trust me, and you can then see that the conditional entropy of x given y is exactly 11 divided by 8, measured in bits. If you want to test yourself, compute the conditional entropy of y given x, maybe without looking at the slides, except for this conditional probability table here, and test this a little bit. Through this, you can now also compute the joint entropy of x, comma. Bring out a pen and paper now and try this out yourself, and then let's see each other again in the next session.